Alright, so this video we're going to be discussing, it's called the mean value theorem. It's very straightforward. It's really common sense things. A lot of things in math, higher level classes, you see them and you're like, I don't know. Sometimes they're hard. You can't really understand where they come from. This one is so easy. It's not even funny. Okay? So, Dad lives about 300 miles from me. Give or take, it takes me 5 hours to get there. Okay? Roughly speaking. Well, you're like, well, Jay, you went 60 miles an hour. No. My average rate of change was 60 miles an hour. Okay. Now, how do you know that? Well, you started here at 0, 0. And sometime later, you're at 530. And now you're like, or 5300 rather. Now, I could have started at 0, 10 and finished at 5, 310. But total, I went 300 miles. Now, I will submit to you that I did not drive on a straight line from there to there. That's ridiculous. Clearly did not. Because when I pulled out of my driveway, I did one of these numbers, and I sped up. And then, I'd get out of town, I sped up a little bit. And I went kind of at a constant rate for a while. And then I got to Portland, I had to slow down. And then I sped up. And then here, clearly I stopped and went to the bathroom for a while, apparently. Yeah, notice I never really doubled back on anything. I just kind of kept motoring along, whatever. Okay. One time, when the kids were really little, I'll never forget this because it was the most ridiculous thing I've ever seen. Back out of the driveway, she says, "Did you get the diaper bag?" Oh, crap. Whatever. Then we take off again. Did you remember that? Oh, Judas Priest. Okay, here we go. Get down the street a ways. Oh, for gosh sakes, here we go again. All right. Oh, stop and nurse. Go a little further. Oh, change the diaper. Okay. And it was like that the whole way to his house. It was the most ridiculous trip ever. And literally took me just a skosh under 5. Just right at 5 hours. Maybe it was a little bit more, but whatever. The idea being is you could draw a straight line from here to here. I'm going to use a different color. I could draw a straight line from there to there that is showing me going at that steady clip. Okay? But what you have to know is that along that time frame, there were times when I was going a lot faster. There were times when I was going negative. There was times when I was going 0. But when you average it all out, we averaged rate of change 60 miles per hour. Now what the mean value theorem says is this, that between A and B, okay, so B and A, and you're like, on a continuous function? Yes, on a continuous function. On a closed interval? Yeah, closed interval. Again, would be kind of hard to figure this out if it was not a closed interval. And why is that? Well, because, you had to start at your house and finish at Dad's house. You had to know where those two endpoints were. And without a continuous function, things get screwy, right? I mean, you're driving to your dad's house, all of a sudden you're teleported somewhere. I mean, that's ridiculous, okay? So you're driving down the road, it's a continuous function. You're between your house at 0, his house at 300. You are somewhere between 0 and 300 the whole way there, okay? What the mean value theorem says is this. There is at least one place in this interval from A to B, there is at least one place when you were going the same speed. I'm going to say speed because that's what we're talking about here. Or, in other words, the same slope as the average value. Well, look at right there. Look at that slope right there. Well, by God, right there, it looks like I have the same speed. Maybe instantaneously. Right here. Right there. Right here. Right there. Or don't forget him. And how about here? And hope I don't miss anybody. There's one, there's one, there's one up there. And the idea being is that there's at least one place where you're going that average speed. That's all it says. So because we're in a calculus class, and as you well know, when in doubt, take a frickin' derivative. Okay. In this situation, I don't know what that function was, but in the homework, you'll be given some function. 2x cubed plus 3 square root of x on the interval from 1 to 9. Okay? Because why not? And so, First thing I got to do is I need to find the slope, right? Because that's what we said. We said that at some point, the instantaneous rate of change, or in other words, at some time, we will be going the same speed, right? Even if it's instantaneously, the same speed as the average rate across the whole thing. Okay, so my first thought is, let's take a derivative. You can't go wrong taking a derivative. So you're going to get 6x squared, and this is going to become 3 over 2 root x. Okay? This is a slope. That is an equation that describes the slope at any point. What I need to find is, what is my average rate of change? Well, I don't know. I would need to know what 1 comma something is, and I would need to know what 9 comma something is, so that I could find the slope between those 2 points. So put a 1 into here, and you're going to get 2 plus 3 is 5. But a 9, oh geez, why did I use 9? 9 cubed. All right, everybody, it's 729 times 2 plus 9. 1458 plus 9. 1467, I think. Okay. I happen to have Desmos up, so I'm going to pull that up. So 2x cubed 2 times 3 cubed plus 3 squared root of 3. Wait, oh, 9, you idiot. I was going to say, I can't be that far off. What's the square root of 9? Which is just 3, which is... Oh, for God's sakes. Stop it. There we go. 1467. I should have just trusted my gut on it. Whatever. Okay? So, if I found the slope, that's 1467 minus 5 divided by 9 minus 1. So, 1462 divided by 8. 182.75. So my average rate of change is 182.75. Remember, that's your average rate. Now the question is, the mean value theorem said, hey, take your derivative and set it equal to the average rate of change, because at some place in that interval, at least one place, they will be equal. Now, if you can solve this by hand easily, you are a better person than I. Okay? Yeah, I mean, in theory, you could multiply everybody by 2 square root x and then square it. Oh, my. This is not Algebra 2, friends. I believe in giving some cool problems that are, well, somewhat hard to solve, so that you can use your calculus skills, not necessarily your algebra skills. There will be time, there's a time and a place always for algebra, of course, duh. But there's a situation where when it gets too messy, you need to know when to deal with life. Now, we said we were on the interval from 1, right, to 9. So why on earth would I go looking outside that boundary? I wouldn't, okay? And so there, oh, for God's sakes, I'm so dumb. Let's try that again. From 1, I said, to 9. Pay attention, Jay. Now, the reason it looks screwy is because our y's are ridiculous. Now, what is the y here? Well, the y is our slopes. Oh, get on there. Now, we happen to know that we're interested in something around 182, yes? So I'm going to do like 180. And, of course, it doesn't like that, so I need to go from 180, let's say, up to 200 or something. What? Now, watch what I do here. I'm going to graph y equals 182.5. What? And look at this. Between x equals 1, which you can't see very good over here because it's right on an edge, and over here to x equals 9 on the other end, the question says, or you remember the theorem actually says that there is at least one place between 1 And you can also do this if you like better. X equals 1. Your choice. I don't care. And then x equals 9. So instead of restricting the domain the other way, you could draw the lines up and down on the screen, something like that. But anyway, here's the deal. Between 1 and 9, the green line, which is our slopes, equals the actual value of the slope, the average value, at least one place. And in this case, it's exactly one place. When x equals 5.05, okay, that's when you get the actual, that's where the average value or the mean value occurs. So when x equals 5.05. Now, let's do this in Excel, or not in Excel, in the Desmos. Let's go back into this deal. And let's graph the original function, which was, what, 2x cubed, I think? Plus 3 square root of x, I think. Excuse me. Let's go make sure that's right. I hate making dumb mistakes. Yes. Excellent. Now, we happen to know that we started at this point and we went to that point in essence, yes, at the corners of our intervals. So I'm going to graph the point 1, 5, which of course you will not see because it's way down the screen. We'll go look at it in a minute. And the point 9, 1467, I think we said. Okay. Now let's zoom out a little bit on this deal. Let's go. Remember, now we're not graphing the slopes anymore. We're graphing the actual values of y. So this time I'm going to do this. I don't know, 1490, I guess that works. Cool. And what you'll see is it hiding up there somewhere? Do you see that point up there? The green point? Okay. We could actually write an equation for this guy. And so because I'm lazy, I'm going to use the slope. We said the slope was 182.5 sorry, back to train up. 182 parentheses, and then one can do x minus 1, I said, plus 5. And the idea by doing that, when I'm doing that, is this. You'll recall sometime back in your career, you may have learned this formula. So m equals y minus y1 over x minus x1, correct? Oops, x1. If you treat this as a number and then multiply both sides by it to clear the denominator, what you will end up with is y minus y1 equals m x minus x1. And then you could do y equals, then you add this fella to the other side, and you will get this. Now, why did I choose the one point that I did, not the other one? Because I felt like it. I could just as easily have done the other thing. So I did 182.5. And then I had x minus, I could have done x minus 9 plus 1467. It would also have gone through the same point. But the reason I show that is not because you have to do it, because it actually makes the learning a little more interesting. So we said that right here at 5.5. So x equals 5.5, I think is what I said. Right here, if you look at the slope right here at this point, the slope of this red line right here is approximately equal to the slope of the orange line at that point. It's approximate. It's pretty close. Now, if you recall, we said it was at, did I say 5.5? I think I said 5.5, didn't I? Pretty sure that's what I said. And it was 5.05. I lied to you. Oh, my word. I'm so embarrassed. How about we put an O in there? Okay. Nice. Anyway. I'm going to pause you for just a minute. I must have written something down wrong. Okay, I had it kind of close. It was 5.505. Okay. So, I'll put this back on. 5.505. There we go. So right here where they intersect, right? If you drew a tangent line right there, well, Jay, wait, are you saying that I should do this? I mean, again, only to visualize it, because, you know, I don't have to do this for the assignment. I think it maybe is helpful to envision it. So parentheses x minus 5.505, right? plus, I forgot what it was. Where's this point at? 340.697. Oh, Jiminy Christmas. Or thereabouts, okay? Look at this green line, okay? Look how that green line right there is coming in as tangent, perfectly tangent right there. At that point on this red line, that is when I am going the same speed as what I would have been doing if I had just gone as an average speed. That's literally all the mean value theorem says. That's all there is to it, okay? And again, the only reason I graph that, it takes time to graph it, is I think it helps sell the bit a little bit and makes it maybe easier for a person to understand. I'll do another couple off the homework. You'll see what I mean, how easy they are. They're not very difficult. You might see this one, for instance, e to the x minus x. Again, that's a continuous function. They have to be. Okay? All right, I need y prime, of course. So that's e to the x minus 1. And then I need points. So I put negative 1 in. Oops, I put negative 1 in, and I get 1 over e plus 1, whatever that is, okay? And I'm going to write it like that because I'm pretty sure in a minute, some of that's going to cancel out. When I put 1 in, I'm going to get e to the 1, which is e minus 1. So when I go to find my slope, what I'm going to find is this. I'm going to take one of them minus the other one. So I'm going to do e to the first minus 1 minus 1 plus 1 over e over, and then it's 1 minus a minus 1. Now, when you distribute the negatives, the 1's going to cancel out, and you're going to be left with e minus 1 over e divided by 2. Now, again, I don't know what that is, so I'm going to look at my calculator. Wish I had my other one out, but oh well, we'll do that in a minute. Come on, go away. Yes, here we go. So, e to the 1 minus e to the negative 1, right? Divided by 2. And 1.175. Okay? So this is 1.175. This is my average value. The question is, when does the slope equal that? Okay? And so, again, this one's not hard to do. I add that. I'm going to get 2.175 equals e to the x. Take the natural log of both sides. I get x equals ln of 2.175. You know, whatever that is. And so if I do that, the ln 2.175, so 0.777, that would be my x value. Okay? First of all, note that is on my interval in question, as promised. As promised. So let's go look at our function. So our function was e to the x minus 1. Okay? It should also be noted that e to the x minus 1 is an increasing function. That is, it's going uphill. So it shouldn't shock me that my average value was positive at all. Okay? Excuse me. Oops, e to the x, wait a minute. What was it? E to the x. My original function was e to the x minus 1. I mean, minus x, rather. E to the x minus x. Okay? So e to the x minus x looks like this. And if you zoom out, it looks like this. Now remember, we are interested in the interval between -1 and +1. Right? That's where I'm interested. And so if you put a point there, which is at that point, right? That's what we said. That's 1 over e. And we put a point at that point right there. Okay? Oh dear. Oh dear. Can you all see what happened? Oh my. This is terrible. This is awful. Did you see what I did? That's disturbing. No, it's not. Yeah, no, it is. It's horrible. Let's try that again. Just slightly. Next time, yell at me when I make a mistake. No, it's the worst part about an online class. Sometimes you will see something happen. Sometimes I'll erase that so you'll never see that. Actually, that was... Okay. Come on, Jay. You can do it. It was right. Why are you... It's been a long day this week already, okay? It's been a long day. Okay, now, back over here, we were right all along. And again, if you play the game that I did last time, again, for your own personal edification, we found that our slope was, what did we say it was? Our slope was 1.175. So if you come back over here and put in y equals 1.175, parentheses, x minus a minus 1, or in other words, plus 1, right? Oops, shoot, plus 1. Okay, and then how high do we have to go up? Well, on this graph it was, you see, 1.368. So plus 1.368. Oh. And then now, if you look at x equals, because we said x equals 0.777 right there. If you drew a tangent line through this point, tangent to the black curve right through there, it would have the same slope right there, same slope as the green line. And that is all the mean value theorem says. That's it. Now I'll do one more where I don't screw it up. And so we'll just go start to finish, and you're like, oh, that was easy. It is easy. It is very easy. Okay? And so, let's see here. Maybe one that's interesting. Yeah, that one. Yes. No. Yeah. That one looks good and interesting. Cosine of x minus sine of x. Y equals cosine of x minus sine of x. And I'm interested on the interval between 0 to pi. Very important that you restrict this one. Obviously, because you need the endpoints, obviously, for mean value theorem. But think about what sine and cosine are doing. They do this forever. They bounce back and forth forever. There's going to be a gazillion times, all right, literally, where you'll have the same slope value. So that's why I mentioned that. All right, if you plug 0 into these guys, so you're going to get the 0, and then the cosine of 0 is 1, sine of 0 is 0, so 0, 1. And then, of course, 2 pi is going to give me the same value, yes? Right? It's going to also give me 1. Because the cosine of 2 pi is 1, sine of 2 pi is also 0. Okay? Well, wait a minute. Wait a minute. 0, 1, 2 pi, 1. Hey, slope is 0, yes? In other words, you're interested in where the average value, you want to know where the average, in other words, the average value is 0. I don't know what happened. Did it do this? I don't know. But it started here and it ended here. It's as if nothing changed. The average rate of change was 0. Okay? So I take y prime, and I'm going to get minus sine x, all right, minus cosine x. And I'm interested in where that sucker equals 0. Now this is one that happens to have a nice, easy solution, so I'm going to go ahead and do it. I'm going to move this fellow over here. So sine of x, or minus sine of x, equals positive cosine of x, right? And then watch me divide both sides by cosine. This is an old math trick. I mean, it's something we teach people, but it is literally a trick. That's all it is. Because sine over cosine is tangent. And what I'm interested in is where is the tangent, really, is what I'm asking, of x equal to negative 1. Well, of course, that requires us that we do an inverse tangent. In other words, what angle has a tangent of negative 1? Well, if you are good with this stuff, you recall that inverse tangent is defined between negative pi over 2 and pi over 2, not exclusively. You're not inclusively because you can't include those values, so they don't exist there. Negative 1 is here, and you're like, hey, what value is that? Well, it's pi over 4. Negative pi over 4, rather. Okay? Negative pi over 4. Now, your first thought is, well, Jay, you're an idiot. Well, thanks, by the way. That is not between 0, which is here, and 2 pi. Well, you're right. It isn't. So let's keep going. So I drag this baby out. I go over another pi. That puts me at 3 pi over 2. Okay? So here's another one coming up like this. Okay? Here's our -1 still. These are pi units apart. So if I add pi to that, I get 3 pi over 4, which isn't surprising because if you're a unit circle fan like I am, here is -pi over 4. If you add pi to that, it puts you in the second quadrant. And in the second quadrant and the fourth quadrant, tangents are negative. So that's cool. But you go, well, wait a minute. 2 pi, why that's, I mean, if you add another pi, that's going to put me at 5 pi over 2, which is, so 1 pi over 2, 3 pi over 2, 5 pi is over 2, right? And then you go, well, can we keep going? Well, yes, there'd be another one at 7 pi over 2. And then, of course, there'd be another one at 9 pi over 2. 9 pi over 2, right? Now, remember, it does this. So here was 0. Here is pi. 3 pi over 2. Here's, oops, I'm sorry. I got a little carried away there, didn't I? There's 2 pi right there, which is not a big deal because I want to show you this. So, and then there's another one right there. So if I go over from 3 pi over 4, okay, so my answers are, so this one doesn't count, right, because it's not in the range. So 3 pi over 4, and then if I add pi to that, well, that's going to be 7 pi over 4. Now I can keep going because this sucker keeps doing this all day long, right? And you just keep adding pi. But this one and this one are the ones that I'm interested in. So let's go look on the graph and let's look at it. So what did I say? Cosine minus sine, I think I said. So cosine of x, oh, come on, get in there. Cosine of x minus sine of x. Okay. And again, I'm interested between x equals 0. And you don't have to do it this way. Again, you can restrict the domain the other way if that makes you happier. I don't really care what you do. It's just, to me, it helps me visualize it. Okay. And so if you check this out, it's pretty exciting. We said that we were going to go from where we were doing it on the intervals between, between here, which was at 0, 1, and here, which was 2 pi and 1. The average across there is literally just y equals 0. I'm sorry, y equals 0. Y equals 1. Y equals 0x. What does that mean, right? Plus 1. Okay. And so there's your average value. Well, now where does it have an average value of 0? Right here has a slope of 0. 3 pi over 4. And right there has a slope of 0. 7 pi over 4. Ta-da! So it's a pretty cool deal. Okay. So that's part of what you're going to be doing in section 4.3, the mean value theorem. It's very easy. Another thing you're going to be doing is actually finding what are called critical values. Critical values. It's a very straightforward procedure. Critical values simply take f prime of x, set it equal to 0. It is the value of x, where f prime of x equals 0, which is interesting because that's just what we did on the previous problem. On the previous problem, we wanted to know, right, where was our derivative equal to 0? And where did it occur? It occurred here and here. And on our graph of our actual function, what did we see there? We saw minimums and maximums. Okay? And that is, for the most part, going to be 100% accurate. There's some other things that can happen at critical values. Okay? But what happens is that is where your function has a 0 slope. So in this case, a max. In this case, a min. In the case of this function here, it actually, cubic, this is like the function x cubed. Technically, at 0, it has a 0 slope momentarily. Technically, at that point, it has a 0 slope. Okay? And so, but that's neither a max nor a min. It's not even a plateau. Okay? It's a weird deal. Later on, we can actually define what that means. Okay? But let's look at this guy for a minute. What makes this a maximum? Okay? Well, now a person could say, well, it's higher than all the other points around it, which is totally true. But what we can actually do is look at what's called the first derivative test. And it's very easy. The idea of first derivative is just this. If, so this is the point x equals a. If f prime of x is positive when x is less than a, and f prime of x is negative after x equals a. That is, in other words, it was positive slopes and then negative slopes. What does that say about a? That says that x equals a is a maximum. Because it was going up, now it's coming back down. Well, for this one, if this was x equals a, right here, then you would say if f prime of x is less than 0, oops, stop it, less than 0, for x less than a, and if it's greater than 0, which of course means it's increasing when x is greater than a, we have a minimum. That is, things were going down, they stopped going down, now they started coming back up. That's the definition of a minimum. Notice that this isn't true. Here, it was positive slopes. So you're like, oh yeah, that looks good. It's positive slopes. Oh, and it's still positive slopes. It didn't change. So by definition, that guy there is neither a max nor a min. And it's clearly neither one of those because obviously over here it's higher. Right here, it's higher than these y values, of course, but it's lower than these ones. And you're like, well, obviously that's not a minimum or a maximum. It's neither one. So later on we're going to find out what that's called, but not today. And we're going to talk about this too. So what if f of x was, well, yeah, let's do that one, x cubed. Then f prime of x would be 3x squared. And you're like, well, that's easy. Let's find our, let's find our max or min. Our max or min. Let's find our critical value. So I set it equal to 0, and I find that x equals 0 when x is 0. That's my critical value. Now, what I like to do is I like to just make a number line. I don't like to get carried away. If I didn't know what this graph looked like, what I would do is I'd pick points on this side of x equals 0, because that was my critical value, and I would pick points on this side. And I would see what happens to my slopes. So let's pick a point. Let's do -1. If you plug -1 into this fella, what do you get? Well, you get a slope of 3. In other words, when you are at -1, the function is increasing because it has a positive slope. -1 squared is 1 times 3 is 3. You're like, but I want to use -5. Knock yourself out. -5 squared is 25 times 3 is 75. Whoa, that's really steep. Yeah, it is really steep. And then we know at 0, we've got a 0 slope. So we know it does this. We know it peters off to 0 there for a 0 slope. But what happens at, like, say, x equals, well, 1, for instance? I don't know. 1 squared times 3 is 3. It has a positive slope again. Okay? So because it was positive on this side and positive on this side, this isn't either a maximum or a minimum. What's interesting, though, is this. This function, with the exception of at x equals 0, this function's always increasing, yes? So if I said to you, where is the function increasing, what would you say? Well, you would say the function is increasing from -infinity to 0. Big kids always use this u with no tail on it. That's the union. And from 0 to infinity. Or if you prefer, from -infinity to 0 on the interval, and from 0 to infinity on this interval. Remember, you cannot equal infinity, always a parentheses. And here, it's not increasing at 0. It has a 0 slope at 0. Okay? Oh, let's do another fun one here. Hey, this function here, we know what f of x equals this fellow looks like. Okay? Where are the critical values? I don't know. Again, when in doubt, take a derivative. It's the easy answer to this problem. So x is equal to -3. So on a number line, here's x equal -3. I'm going to pick a point over here, and a point over here, because we know that here we have a 0 slope. But I want to know what happens on either side of that. Okay. So I'm going to use -5. Okay? Don't put it into the original. Put it into the slope formula. 2 times -5 is -10 plus 4 is -4 slope. Now, I don't really care what the slope is. I just care that it's negative. That means the function is coming down. Here it stops going down because it has a 0 slope. And then what happens over here? Let's do x equals 0 for fun. If you plug 0 into here, 2 times 0 plus 6 has a 6 slope. I don't really care about what it is. I care about that it's positive. Well, that's dumb. I care that it's positive slope. That's all I really care. That looks stupid. I care that it's a positive slope, meaning that over here it's going to be increasing. So because it was decreasing and now it's increasing, we say that at x equals -3, we have a minimum. Nice. What about e to the x? Here's our good friend e to the x. You've got to love e to the x. He's swell. Well, what is y prime? Well, y prime is, well, it's e to the x. Where does e to the x equal 0? Ha! E to the x never equals 0. What do you mean? That means the slope is never 0. Wait a minute. If the slope is never 0, by the way, e to the x is a continuous function on a continuous function. What can you say? Feels like the slope must always be positive or always, or, oh, that's disgusting, always negative. Okay? Now you're like, well, what number should I pick? It doesn't matter. I'm going to choose x equals 0. But you can put any number into here. When you put 0 into the slope, what do you get? Well, you get e to the 0, which is 1. In other words, I have a positive slope. Well, again, because it's a continuous function, they're either all positive or they're all negative. In this case, they're all positive. Wait, if the slopes are always positive, slopes always positive, that means the function is always doing what? It means the function is always increasing. Well, if the slope is always increasing, we need a math name for that. And so what we say is it's monotone, increasing function. Your book uses the term the monotonicity. That is, it doesn't change. It's always increasing in this case, or it's always decreasing. Okay, that's all that means. It just means it doesn't change. Okay. Well, can you think of any other functions that are always increasing? One that comes to my mind is the ln of x. Okay? If this is ln of x, well, I mean, you know what the function looks like. It looks like that. It's always increasing. So the idea here is y prime is 1 over x. Hey, where does 1 over x equal 0? Dude, it never equals 0. Well, if it never equals 0, what does that do for me? Well, pick a number. Remember that this domain is x bigger than 0. So any number bigger than 0. So I pick 2. If I put x equals 2, then I get 1/2 for our slope. Okay, this is my slope. What this says to me is that they're always, again, always positive or always negative. In this case, always positive. So where is this guy increasing? It's always increasing. You could say it's always increasing, or you could just say it's increasing on this interval, which, again, is the whole domain. If you add e to the negative x, I think we all know what that function looks like. Looks like it's a decreasing function. And, of course, again, it's negative e to the negative x. And again, this thing never equals 0. So because it never equals 0, there are no critical values. So it's either going to be always increasing or always decreasing. Well, look, it doesn't take a brain surgeon to figure this out. This guy's always positive, but then there's a negative in front. So your slopes are always negative. In other words, this is a monotone decreasing function. Always decreasing. And that's the essence of section 4.3. It's pretty straightforward. Finding critical values, using the first derivative test on them, talking about just learning the idea of what does monotone increasing or decreasing function mean, and the mean value theorem. Okay, mean value theorem is pretty handy for the most part. The places where it will show up in most of your lives in an application sense of the word is the idea that when you look at something, you're like, well, look, our average rates of change are doing this or that, or we have an average rate of change from start to finish of this much. Then you could talk about, looking at it and seeing how much the function changes around and stuff, and does that seem reasonable, or when did we have that? And so, like, this would be a point maybe that's interesting to us for some reason. Okay, it's very much a conceptual thing. It's not a lot of you don't use it a ton, although it's used in a few proofs from time to time. Which I hope you can count yourselves among the lucky people that doesn't have to do a lot of proofs in your life, because they aren't much fun. Anyway, there we go.